right, so we are looking at the simple harmonic motion assignment. So this is going to cover everything from like period is 1 over frequency to t equals 2 pi times the square root of L over G for a pendulum. T equals 2 pi times the square root of M over K for a mass on the spring. Okay, there's going to be some Hooke's law, some conservation of energy. That's it. That's what's in there. Okay, it's like 4 days worth of material, right, in this assignment. So, again, look at the point values as always. Okay, remember important things like significant digits. Now, new or review of a rule to do with significant digits. Significant digits are any measured value. Yes? Okay, things off the formula sheet, absolute. Counted numbers. Are counted numbers measured? No. If they were, I would have said measured numbers. Counted numbers are not measured numbers. Therefore, they contain no uncertainty. If I count the number of people in here, I can be, well, at least reasonably certain that I counted right and that that's how many people there are in here. Okay? So, if a pendulum is oscillating back and forth, and I count that it makes 4 oscillations, I am 100% certain of that number. It isn't a measured value. I counted it. Okay? And counted numbers do not affect your significant digits. I don't see a lot of people writing that down. It's a big piece of information because it's like relevant on several questions on this sheet. Okay? If a number is counted, especially things like the number of oscillations, that is a counted value and does not affect your significant figures. All right, so for question number 1, the period of a simple pendulum is to be 2 seconds. What should be its length? We will assume said pendulum is on Earth. Okay, that's another important piece of information for that question. Okay, because it gives you that one other given that you need. All right, so don't overthink that one. Question number 2 is asking about a grandfather clock whose length, okay, is 1 meter and keeps accurate time where G is 9.83. Then the people move, and they go to a place where G is now 9.78 meters per second. And we need the pendulum to still keep accurate time. Pendulums can be adjusted, right? Specifically, their length can be adjusted. So this pendulum needs to have a different length. You need to calculate what that is, right? So you may need one piece of information from the first pendulum, okay, to help you get the new length of the pendulum for the new location. Okay, and number 3, astronauts on a distant planet set up a simple pendulum, and it executes simple harmonic motion and makes 100 complete cycles. Counted or measured? Counted. They counted 100 oscillations. That's a counted value. Okay, in 280 seconds, is that counted or measured? That's measured. Time is measured. Okay. What is the acceleration due to gravity? Okay, don't overthink that one. Probably shouldn't be a 5-mark question. Okay, question number 4. Wrecking ball is hanging at the end of a long cable on a crane. So this one here you really have to picture in your mind. A bright student, so one of you, okay, wants to estimate the length of the cable and therefore improvises by using a simple pendulum made from a half a length of string and a stone. So he's got a small pendulum that's only a half a meter long. Okay? The student observes that in swinging back and forth over a small amplitude, the wrecking ball makes 1 oscillation in the time it takes the stone to complete 5 oscillations. Okay? What is the length of the cable? So this is another one where you probably have to do one calculation about the first pendulum and use that to help you with the second pendulum. Okay? All right, and then number 5, okay, another pendulum question. A lot of pendulum questions on like just the period formula. Okay, so find its period, find how long the pendulum would have to be to double its period, and why is this number not just double the length? Like a sentence or 2 explanation on that one. Talk about the formula, the nature of the formula. Okay. Number 6, find the length of a pendulum oscillating on the moon that would have the same period as a 1 meter pendulum oscillating on Earth. And remember that the moon's gravity is 1/6 that of Earth. There is only one measured value in that problem, and it is not 1/6. Okay. All right, number 7. Okay. This one usually gives people a fair amount of trouble because they overthink it. Okay. So this is a mass on a spring situation. Okay. We have the first situation is there's a spring and mass 1 is hanging from it, and it is oscillating with simple harmonic motion with a frequency of 10 hertz. Okay, watch out for being given frequency versus period in a lot of these questions. Not that when like if the frequency is 1 hertz, so is the period is 1 second, but okay, for other ones you got to watch that. Okay. In the second situation, it says when another object of mass 2 is hung on the spring along with M1. So the second situation is the same spring, but now M1 and a second mass are both on the spring. Okay? The frequency of the motion is 5 hertz. Find the ratio between M1 and M2. In other words, how much bigger is M1 than M2? Now, the key part here is it's the ratio. You don't actually need the real masses. Okay? And that's important because you can't actually calculate the real masses. You are missing something that would help you do that. What are you missing in this question? Spring constant. But it is the same spring in both situations. So since it's the same spring, and you're only looking for a ratio and not the real masses, here's your big tip. You can make K whatever you want. Okay. All right, and the other thing to remember is that in the second situation, they're both on there. That's the part that people mess up late in the question. Okay. All right, question number 8. Okay, spring with a constant of 1,526 newtons per meter is oscillating with a frequency of 3 hertz. What mass is suspended from it? Don't overthink that one. It's pretty simple. Okay, it's just a mass on a spring. And so is the number 9. Okay, don't overthink that one either. Okay, it's mounted on the floor, oriented vertically. That makes no difference whatsoever. Okay, a 6 kilogram block is placed on top of this spring and pushed down to start it oscillating. Find the frequency of the motion. Okay. All right, number 10, a bungee jumper is very similar to a mass on a spring. After taking the leap, the jumper oscillates with simple harmonic motion over 30 seconds. Measured or counted? Measured, time's always measured. She oscillates 5 times. Counted or measured? Counted. Okay. The spring constant of the cord is 53.2 newtons per meter. What's the mass of the jumper? Don't overthink it. It's just a simple mass on a spring, period question. Okay, then we are getting into conservation of energy. Okay, so number 11, object vibrates at the end of a vertical spring. Maximum speed of the object is 0.18, and its maximum displacement is 0.14 meters. What's the mass of the object? Okay. And an object vibrates at the end of a horizontal spring along a frictionless surface. Okay, and I think I redid the point values for these on your sheet, yeah? These are only 3 on your sheet, because 6 was ridiculous. Like, really, really ridiculous. Okay, these aren't even conservation of energy questions. Okay, they're energy questions, but they're not conservation of energy questions. Okay, so they're much, much simpler than that. Okay. So I give you the potential energy, and you just have to find the displacement. So you have a formula for potential energy. Okay, don't overthink it. Same thing for this one, except it's kinetic. Okay, the object's kinetic energy is 7.3 joules. What's its speed? Don't overthink it. Okay, you have a formula that calculates kinetic energy as well. Okay, all right, that's it. So probably the one that'll take you the longest is number 7. Okay, that tends to be the one that gives people the most trouble, but the rest of them should go pretty quickly. All right, so we will work on that for about another 5 minutes or so. I know that's not very long, sorry. Okay, but 5 minutes for today, and then all class tomorrow. Okay, to work on it. Yes.